I'm for the first time on such exceptional event that is called adventures in self-similarity, but adventures. And so, what are adventures between two self-similarity? I should speak on two topics concerning two self-similarities, and the third one, parameter estimation, concerns one self-similarity. However, it can be generalized. The results are very recent, and even some of them are in progress. Everybody knows that fractional Brownian motion itself with any first index is self-similar process and with stationary increments. According to geometric terminology of Kaplan, it belongs to helix. Helix is a process with covariance function of the following type. Of course, these properties are very useful, however, very restricted. For example, simple Einstein-Uhlenbeck process starting from zero time point is neither self-similar nor stationary or with stationary increments. Therefore, our goal now is to consider more wide class of Gaussian process with the following property. In the case when first indices equal from the left and right hand sides, but the constants are different, such processes belong to quasi-helix. And in our terminology, when possibly Hurst indexes are not equal, they live between two self-similarities, so this is our main object, or they belong to the generalized quasi-helix of the following way. If to compare them geometrically, this is helix, this is quasi-helix, and this is generalized quasi-helix when we have everything different, constants, and Hurst indexes as well. So we consider three problems concerning such processes: asymptotic behavior of maximal functionals, representation theorems involving integrals with respect to such processes, and some statistical results. The results are common with my colleagues Alexander Novikov from Sydney University, Mikhail Zhitlukin from Stiklov Mathematical Institute, and Georgy Shevchenko and Konstantin Radchenko from our Kiev University. So, what about asymptotic behavior of maximal functionals? Unfortunately, till now we do not know the value of the following mathematical expectation, even if the process X is fractional Brownian motion. At least we don't know, but maybe this result is unknown. So the first problem is how to find analytical bound for such maximal functional or upper limit if we want to have it, or to find analytical bounds for the maximal functional. So we consider more general case in fractional Brownian motion. However, for fractional Brownian motion we can get more precise results. But now we have considered center Gaussian process. Let it be on some probability space. For such maximal estimates, there is a lot of results, and maybe general of them belong to Talagram. We use very widely the results concerning Gaussian processes. However, one moment, Talagram in his results ignored constants, but we need their value at least to know if we compare lower and upper bound, do we deal with 10 billions or do we deal with something like 3 or 4? So the first lemma is some not generalization, but some specification of Talagrand's result. Let we have continuous center Gaussian process on some space of time. And let me have the chain, the sequence of sets, some that we start from one point, and the set with index n have no more than 2 to power 2 to power n points. In this case, we can estimate the mathematical expectation of maximal value of this process in such a way. So this is our chain. And here we have distance between point T and set Tn. And only the question is what is constant A? Can it be estimated? Yes, it can be estimated by very good number. And the value of this constant appears from this inequality. So our achievement is only this constant, but it helps to understand what we have. And now the bounds for the expected maximum. Let me have a center Gaussian process, and let me have some, here is a lower bound. Let me have some constant and some something like Hurst index with the following property. So we have lower bound. In this case, we have corresponding lower bound from mathematical expectation of its supremum, and we see that the order of increasing when h tends to 0 is 1 over square root of h. It was the original question from which the whole work appears. What will be with fractional Brownian motion with its maximal functional when Hurst index tends to 0? From the beginning, we suppose that the maximal functional tends to infinity. However, it is very surprising that computer results show something like 3, not infinity, but 3. And it is very powerful computer system, so it means that in some cases computer do not help. We have a great distance between 3 in computer system and infinity that is in reality. And now upper bound. If we have corresponding upper bound for distance, then we have upper bound for maximal mathematical expectation of maximal functional. It can be obtained with the help of Lagrange inequality, and it has some value. You see that here we have the same order of rows from below and from above. And the constant is very moderate. We have the following estimate. But now we try to understand maybe the reason of computer error is that, of course, we discretize, when we compute something, we discretize time. What will be if we discretize time and approximate the maximal functional? Here are the results. Let me have the same center continuous Gaussian process with lower bound. And let me have n comparing to h, and in mind we know that h can tend to 0, so n in this sense tends to infinity. And in this case we have the following approximation of the whole maximum and the maximum over some discrete sets. And here is the rate of convergence. Of course, if h is fixed, then we indeed get the rate of convergence. Not very fast, but we cannot get something better. But if h tends to 0 and n is compared to h, we don't know what will be. So let us consider some particular cases. For example, if we have fractional Brownian motion, then we can get the same result, but by much more simpler calculations, but the upper bound will depend on A, and A depends on H in this case. The method of proof is very simple. We take the piecewise linear approximation process and get the following constant. You see some calculations are only technical details, but this constant A of H is of the following form. So very simply we get the result for fractional Brownian motion, and we have also if H is constant, the rate of convergence, but if H tends to 0, it can get nothing. Now, how to analyze the situation when H tends to 0? We can show that if we want to have a good approximation, then the number of points should be at least of order A to power 1 over H. So, but A is more than 1. So if H approximates 0, then n of H should approximate infinity. So that H logarithms of NH is bounded away from 0. Here is this result. Let we have a semi-Leo-centered Gaussian processes with such two-sided bounds. This is some function, not simply H, but we denote it as big of H. And let us suppose that the number of points is connected to H, and in such sense that we have at least some approximation. Then necessarily n of H is so big that this lower limit is positive. So it means, of course, that NH should tend to infinity, and we have even the rate of convergence. In the case of fractional Brownian motion, we have very simple conclusion. Let we have two sequences, n of k and h of k of indexes and of number of points. In this case, if nk tends to infinity with any rate possibly slow, and hk tends to 0 also possibly slow, however, maximal functional tend to infinity. We have contradiction with computer results, but we believe in theory more. In the case of fractional Brownian motion, we can give more strong results and some additional results. Especially we can state what will be when h tends to 0, what will be with fractional Brownian motion. So let us consider Gaussian white noise process with variance 1/2. It is the set of IID n0 1/2 distributed random variables, and we should consider such a difference to be more precise and to get variance 1. So if we use some notations for convergence of finite dimensional distributions and for equality distribution, for fractional Brownian motion we have the following statements. Additionally, we see that with h, the function, this is our maximal functional mathematical expectation for t from 0 to 1 of fractional Brownian motion. It is decreasing, it is strongly decreasing in h. We have its values for 1/2 and 1, it is not very surprising. We have the convergence in finite dimensional distribution. Our fractional Brownian motion converges to our process Z. And it is expected that maximal functional tends to infinity. However, as a matter of fact, this part of theorem can be proved without use of property of Gaussian distribution, we need only the fact that this maximal tends to infinity in probability, but it is proved immediately. Also, we can state in this case that for fractional Brownian motion, maximal functional is continuous in H. I should say that our techniques to prove these facts is very simple. For example, here we use so-called Chattery inequality. For lower bounds, we use Sudakov-Vernix inequality, and for upper bounds, Lagrange results, and it helps. So, what about other Gaussian processes except fractional Brownian motion? So, let us consider some examples. The first example is subfractional Brownian motion. It is a center Gaussian process with such covariance function. For example, in the paper of Baidetsky and other authors, it was proved that this process belongs to quasi-helix with the same Hurst indexes but with different constants. Of course, immediately all the previous results concerning the lower and upper bounds and approximation are valid for this process. Bifractional Brownian motion that Kyprian mentioned today, this is the process of the following with the following covariance function. And also we have two-sided bounds for this process. So bifractional Brownian motion in our terminology, but not in our, but in terminology of Kaplan, because he belongs to quasi-helix with the same Hurst indexes. And also for this process, these theorems are valid. Another example is what can we do with Wiener integral with respect to fractional Brownian motion? We consider here only the case, it is worst case when h is lower than 1/2, because for h that is more than 1/2, we shall consider this a little bit later, and it will be clear that of course for h more than 1/2 everything is much more better. So consider the measurable function and introduce the following integral operator. However, here it is a fractional integration. However, h is less than 1/2, so this is not integral but fractional derivative. And more precisely, fractional derivative now has the following form. This is the derivative of integral, but it consists of two terms. According to the papers of Bender and Celine-Jost, under the following assumption, we can transform the integral with respect to fractional Brownian motion into the integral with respect to Wiener process. And it helps us to specify the condition of f that's applied together with this inequality. Condition, for example, of the first theorem, this is the lower bound. So we consider the following process, transform it in this way, and we suppose that some specific condition, of course, but for the case h less than 1/2, it is not so simple to formulate at least some conditions. So we suppose that function is continuously differentiable, separated from 0 in such a way, and also that it is satisfied following condition, more or less artificial. However, we can present many examples of such function. So we have some technical relations for fractional derivative. I omit these technical details, but at last we get the following kernel, which is closely connected to the kernel of representation fractional Brownian motion via Wiener process. Here is this kernel, and so for it we immediately get the equality. It means that for our process we have the lower bound. And so the finiteness of square of the integral of square of function together with our condition are sufficient to have the lower bound in our theorem for lower and upper bounds. Some examples of functions that satisfy our condition is exponent function and even exponent of such form, because we know that if exponent does not exceed h, we can integrate. We can integrate in the following way by parts, and integral exists. So here are some examples of our processes, and now only a few words concerning which techniques is used. Here is Sudakov-Fernix inequality for lower bound, here, and also Sudakov's inequality, Chattery inequality for continuity of maximal functional, and of course Talleyrand and Dudley inequalities for entropy bounds, but entropy bounds are closely connected to chaining rule, so they give the same order. We can use both these entropy bounds, we can use chaining rule, and we get in order the same result. The difference is only in constants. This is the first result concerning what can be between two self-similarities. Other question is following. Let me have some random variable that is measurable with respect to some filtration from 0 to 1, and filtration is generated by some Gaussian process. Can we in this case represent our random variable as the integral with respect to Gaussian process? This question is interesting itself, and of course it's interesting for application in financial modeling, because real markets demonstrate the long-range dependence. So in some cases the standard representations results are not satisfactory and are not sufficient. So let me have, for example, here Wiener process. In this case, everybody knows what will be. For example, the famous Ito representation theorem establishes this representation for center square integrable random variable. Less known is the very recent result of Dudley, who proved that every random variable psi has this representation, but not with square integrable integral. Of course, there is some additional results and many results for martingales and semi-martingales, but now we wish to deal with some more general self-similarities, so we don't concern this. In the case when X is not semi-martingale, is less studied, but we have some results. The first result was established in our paper with Shevchenko and Balkila for fractional Brownian motion. Of course, now every time first index will be more than 1/2, it is principal. We can show that it is principal. The construction for establishing this representation relies on the Hölder continuity, and the small ball estimate is for fractional Brownian motion. However, self-similarity and stationarity of increments was used. But then a very simple question appears. Of course, let me have the result for fractional Brownian motion. But what will be with fractional Ornstein-Uhlenbeck process? It is very close, but it is not neither self-similar, not with stationary increments. And what will be? We don't have the representation, it will be crazy. So we should go away from self-similarity, away from stationary increments. Some additional results were obtained in the papers of Shevchenko and Vitasari, and they consider the mixed fractional Brownian motion, which is the sum of inner process and fractional Brownian motion. However, the idea was that representation can be in much more general case. When we carefully analyze the previous result, we see that they are based on a specific small ball property, but this small ball property for the first is very hard to check, and for the second it is not necessary. It is not optimal. So we try to generalize this result. First we analyze how to get an upper bound for small ball probability for Gaussian processes with variance distance satisfying two-sided power bound. So in our terminology, for the process that is contained in generalized quasi-helix. And second, we analyze precise conditions needed to obtain the representation results. So let me have a center Gaussian process on finite interval with variance distance satisfies our well-known two-sided power bounds, but we separated them. Of course, we understand that this Hurst index, let it be Hurst index, as usual, exceeds the second one. Another supposition is that the increments of the process are either positively or negatively correlated. Better than that if they are positively correlated, of course. So we suppose the following inequality for plus or for minus. For small ball property, we can get the results for both sides. But for representation results, plus is better. However, Gisanov theorem permits to get the results for minus because for it does not matter. Some remark concerning indexes. If we have, for example, the lower bound and yes, here is the lower bound. If we have lower bound and positive correlation of increments, then we have that necessarily Hurst index H1 exceeds 1/2, or at least equals. And similarly, if we have upper bound and negative correlation, we have that H2 is less than 1/2. So the first result in our direction, this is lemma that establishes an upper bound for small deviations of the process X. Let me have a Gaussian process satisfying only A1 and A2, and additionally, if we have B plus, so positively correlated increments, then we have such upper bound for the probability to be inside small ball. And if we have negative correlation, then we also have the probability, but it is a little bit worse. The small ball estimates, of course, they are useful only when the exponents of epsilon here and here are negative. In the first case, it happens when we have such a relation between Hurst indexes. We know that H1 is more than H2, however, this is a restriction from the other side. And in the case 2, if we have such relation, I only recall that we have such relations for both Hurst indexes, and of course, this is a relation between two of them. If we want to get the representation result, we need in small ball probability on any interval, and this is some more or less technical result, but it stands that we can get the small ball estimates on any interval. These small ball estimates are got with the help of the results of Li and Shao. However, all the authors restrict themselves to the self-similar examples. But our goal is to avoid self-similarity, and it was surprising that we can get these results and with some additional efforts, but they hold. Some examples when we can take these results and to which class of process we can generalize the results for fractional Brownian motion. Of course, we again consider the integrals with Volterra kernels, for example, with respect to Wiener process. So, what are the conditions of the kernel? We want to establish the results for positive correlation. So we suppose that the kernel is non-negative. It is non-decreasing in the first argument, and it is Hölder in some sense. Here we can have some weakly singular multiplier. Also, some the kernel themselves satisfies the same inequality in some sense, and for upper bound, here we have upper bound. For the lower bound, the situation is that we have a choice for such a difference or for one of the conditions can hold. And the condition for kernel itself, it is understandable, because when we use the upper bound, we want to estimate every term. But if we want to get the lower bound, it is sufficient to estimate one term, and the other terms are simply positive. Then, if we have such conditions, this one, and one of these, then the Gaussian process F, that is integral with kernel K with respect to Wiener process, satisfies conditions of our two-sided bounds and positive correlation. And so for these processes, we have trust to get representation results. Also, some results with respect to integration. Here are some example, and we see the following situation. When we have the kernel, if we omit here additional function phi, we get the kernel which represents fractional Brownian motion via Wiener process. But if we multiply by this function, immediately we can get corresponding integral, but all the properties of self-similarity, stationarity of increments disappears. However, this function phi, if it is restricted in such sense from below and from above, it helps. We have no problem with this function with our results. So we also consider the integrals with respect to fractional Brownian motion, but if we want to keep positively correlated increments, we should restrict ourselves to the case A is positive. So in this case, we can get all the results and with positively. And so our process satisfies conditions of above theorem. So this is only preliminary works, but concerning the representation itself, we use all these preliminary results. So what are representation theorem for Hölder continuous Gaussian processes satisfying small ball estimates? So the situation is following. We establish small ball estimates with some condition, and now we proceed with these estimates. and we forget about our conditions. So we introduce condition of Hölder continuity, but with some power that exceeds 1/2 at this principally, and we take the small ball estimate of the form that we established previously. So let our conditions hold, and there are some remarks concerning the relation between the constants in our representation, lambda, mu, and zeta. They cannot be arbitrary. So this is the main relation between them. But if theta is fixed for our process, mu and lambda are more or less free to choose. So we are more or less free to choose them. Now, since we want to construct the integral with respect to Gaussian Hölder process, now only Hölder property is important, not Gaussian property. We need to define the integral with respect to Hölder process. It is some aspect of fractional integration. So we need some elements of fractional calculus, but I don't present all of them now because they are more or less known. But the main statement is that we can integrate with respect to process J the function f, here is now also the function, if they have corresponding fractional derivative, and fractional derivatives are integrable. This is so-called generalized Lebesgue-Stieltjes integral, which was introduced by Rascanu and Noël and by Martinacelli, and now are widely used. And I must say that in the case when we want to apply our results to financial modeling and financial hedging and pricing, of course this integral is much more convenient than, for example, Skorokhod integral, because for financial people it is impossible to consider such complicated integration as Skorokhod integration. But this integral corresponds to the strategy buy and hold, and so we can consider it more or less simple, in spite of the construction is very complicated. But we know that if integrand and integrator are Hölder and the sum of orders of Hölder property exceeds 1, this is simply the limit of Riemann-Stieltjes sums. So I shall present only the main results in this representation, where the first result is the following, and this is key point in proving the representation result. Let me have an adapted process F that satisfies our condition, Hölder condition, and small ball property. Then there exists an adapted process phi with fractional norm finite, such that for it is finite for any t less than 1. However, the limit of the integral from 0 to t is infinite. This is a result with the help of which we can construct step by step the representation function, and so with this result we can state the main theorem. The main theorem is the following. Of course, it is more or less surprising for the first glance, because we suppose that we have adapted process that satisfy our Hölder condition and small ball property, and a random variable, but here is a more or less surprising property. We state that this random variable is a finite value for some adapted process Z, that is Hölder. And the Hölder power of this process should be more than such constants connected with our process X. So process X has constant mu lambda theta, but psi must be the final value of the process with Hölder property of such power. Then we can state that there exists an adapted process phi, or it will be psi of course here, such that we have the representation result. Of course, we can consider the case when rho is comparable to theta, because it's more interesting case. And as a corollary, we can state that if we have adapted Gaussian process that satisfies, at last we can connect our previous results with this one. Let Gaussian process satisfies condition A1 lower bound, A2 upper bound, and positive correlation of its increments. But this is the relation between Hurst indexes. And let we have random variable that is final value of such adapted process with such Hölder power that exceeds rho 0, and the rho 0 is connected to our Hurst indexes. Then at last we have an adapted process. Of course, every time it will be the same side and side. So we have this representation result. Unfortunately, this property of random variable to be the final value is unavoidable. It is very close to necessary condition. So I shall omit other details, and I shall omit, of course, parameter estimation. It will be for the next time. And after many slides, thank you for the attention.
Thanks so much, Yuliya, for this very nice talk. Are there any questions or remarks? So I was wondering, so you mentioned that there may be some application in mathematical finance.
Yes.
And if I remember, so in the case of the fractional Brown motion, for the pricing of derivatives, there is an issue with arbitrage.
Yes, but it is another story. We now know how to avoid this property to be arbitrage.
Enlarging the filtration, you use the same device, the Patrick editor.
No. In general, the question of hedging is more general. You can hedge even if you have arbitrage possibility. But how to deal with arbitrage, it is a long story. For example, we can consider mixed model, and immediately arbitrage disappears. We can consider discretization, and arbitrage disappears. So, of course, we cannot avoid this situation with arbitrage itself. However, we know some ways how to deal with this.
You said your condition was almost necessary?
So
the fact that the variable psi has to be C1 for some number.
It is very close to necessary.
Because the stochastic integral representation itself has that Hölder regularity.
The process can be arbitrary. The process have no relation to our representation. Let it be at least some. For example, if you take constant, you can take the process constant, and it is enough. So you can represent any constant. The process is arbitrary. Constant is good. Of course, if the final value is constant. Yes, this condition is surprising, I understand. However, it is very close to necessary, and to be necessary, and it is not so meaningless as you think for the first time. The constant demonstrates this.